So welcome again to the new problem solving session. Now we will try to solve some numerical problems on quantum mechanics. Subtopics is linear algebra and formalism. Okay, so let's start. So this is the first problem from JEST 2012. Problem says that for an n cross n matrix consisting of all ones, that means the order of matrix is n into n, okay, and all element of that matrix will be 1. So 1 comma 1 comma 1 dot 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 up to n times. Similarly dot 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 diagonal elements, n number of diagonal elements up to n. So for this type of matrix, what will be the eigenvalues? Okay, so we know that if there is a property of important properties of matrix, if two rows or two column are related or same, like if r1 or r2 is some integer multiple of r1, or c2 some integer multiple of c1, or any row or any column are interrelated in this way, or if rows are and columns are identical, for that case eigenvalues are all eigenvalues are 0 except 1, and that one eigenvalue is trace of that matrix, that is here since it is n cross n matrix, so there will be n number of diagonal elements and all of them 1, so that's why addition of n number of ones, it gives n. So eigenvalues, one eigenvalues is n and others are 0. So next problem, the coordinate transformation is given. Now we have to find out that this transformation will be a translation or a proper rotation or a reflection or not any of them. Okay, so let's write this in terms of matrix. Okay, x dash to y dash equals to 0.8, 0.6, then 0.6 minus 0.8 into xy. Okay, so therefore this will be the transformation matrix. Now we are only talking about this transformation matrix. Let's find whether this matrix is orthogonal or not. So this is as T, so T is the matrix, or we can take okay, transformation matrix T. So T is given as 0.8, 0.6, 0.6 minus 0.8. Take transpose of this matrix. So transpose of T, it gives 0.8, 0.6, 0.6 minus 0.8. If we multiple them, that is T and T transpose, it gives 1 0 0 1, that means 1 identity matrix. So we can say that this matrix, that is T matrix, this transformation matrix is orthogonal matrix. And this is the first things we have to check. Second things we have to check, that is the what is the determinant of this transformation matrix. So if we find out determinant of T, it gives minus 0.8 squared minus 0.6 squared, so it gives minus 1, so determinant is negative. Okay, so whenever this transformation matrix is orthogonal and it gives minus 1 determinant, that is determinant minus 1, that always indicates that it is the transformation is basically the transformation represents reflection only. Okay, for reflection only. Okay, now for rotation we know that rotation matrix sin theta cos theta minus, sorry, it will be cos theta sin theta minus sin theta cos theta. So this is also a transformation matrix, and it gives a proper rotation, because if we take the determinant, then it gives plus 1, determinant of this determinant of this matrix, it gives plus 1, and also it is orthogonal matrix, so that's why it represents proper rotation. But here this matrix, this transformation matrix is orthogonal, okay, but it gives negative determinant value, -1, so that's why it represents translation. So answer will be option C only. Okay, this is the answer. Next question, Hermite conjugate of this operator. Hermite conjugate, we have to find out the Hermite conjugate of this operator. So in general, for Hermitian operator there is a expression. If if any operator satisfy that expression, then we can say that operator is Hermitian operator. So what is that expression? That is integration psi star a is that operator, phi dx. Let's take phi and psi, both are function of x, and it gives a psi whole star phi dx. Now find this part only. So integration psi star a is operator, that is minus del x, so it will be del phi del x and dx. So take the negative sign out. Psi star del phi del x dx, integrate by parts. So first term gives psi star, then phi, limit will be there, and minus plus, then it gives del psi star by del x, del psi star del x into phi dx. Okay, so this term gives 0 if we're talking about if we consider only the boundary value on the boundary limit. So at the boundary it gives 0, so 0, and the last term will be this can be written as del psi del x whole star phi dx. So if we compare with the exact formula, this is AB, this is A, and this is B, we compare A and B, then we can easily say that A, we can easily say that the conjugate, Hermitian conjugate for this operator is del x only. So del x will be the answer. Okay, next problem. So if the expectation value of momentum momentum operator is p for the wave function psi of x, that means if we operator momentum operator on psi of x, it gives expectation, this is the expectation value, and again psi of x. Okay, now we have to find out the expectation value of to the power iota kx by h cross into psi of x. So operate on e to the power iota kx divided by h cross psi of x. So this is basically p is nothing but minus iota h cross del x. So we can this is an operator, so operate it like by parts u into v, and then we get exponential part, take it as it is. Okay, derivative of this psi of x, so operate p operates on psi x only. Okay, then plus derivative of this iota h cross minus iota h cross is always there for operator p, and if we derivative exponential part, then it gives iota k by h cross, then exponential part as it is. Okay, and psi is also there, so psi is also there. Okay, sorry, so psi is also there. So now this is psi, this is also psi, so this part, if we operate on this, it gives what, p expectation value we can take out, and then this into psi of x, e to the power iota kx by h cross psi of x. Okay, and here we get this part as it is, and if we multiply this, h cancelled, iota iota minus 1 and plus 1, so plus k, again this function e to the power iota kx by h cross psi. Now if we take this is as another function, that is phi, so you replace p phi equals to p plus k into phi of x. Ultimately we can say that the expectation value of momentum for this wave function basically p plus k, so option C will be the correct one. Okay, next problem, Hamiltonian operator for two state system is given, and alpha is a positive number with the dimension of energy, and the energy eigenstate corresponding to the larger and smaller eigenvalues respectively. Okay, so for this problem we have to write first the matrix form of this matrix form of this Hamiltonian. So what will be the matrix form of this Hamiltonian? Alpha 1 state, so what will be the uh, coefficient? That is 1 for this state, coefficient is minus 1 for this state, 1 2 1 for 2 1 1. So this is the matrix form. So from here we have to find out the eigenvalue. So determinant of h minus lambda I equals to 0, characteristic equation. So from here we have to find the eigenvalues. So simply alpha minus lambda, then 1 1 minus 1 minus lambda, determinant equals to 0, cross multiple here, sorry, alpha, so minus alpha square minus lambda square minus alpha squared is 0. So if we open this, then here we get lambda square is nothing but 2 into alpha squared, so lambda will be plus minus root 2 alpha. So these are the eigenvalues, plus root 2 alpha and minus root 2 alpha. So for plus root 2 alpha we have to find the eigenvectors, and also for minus root 2 alpha we have to find the eigenvectors. So ultimately we get two eigenvalues. Okay, now remove this. So we have two eigenvalues, one is lambda 1 root 2 alpha and another is lambda 2 minus root 2 alpha. Okay, so let's find first for root 2 alpha. So for root 2 alpha, the eigenvectors will be, so this is alpha minus root 2 alpha 1 1 minus 1 minus root 2 alpha into x1 x2 0 0. So if we want to find the relation between x1 and x2, it gives alpha into 1 minus root 2 into x1 plus x2 equals to 0. That means x2 is nothing but alpha will be there, so alpha cancel, so x2 is nothing but root 2 minus 1 into x1. Okay, so if we want to write this form in terms of matrix, we can write, but we have to write in terms of these state vectors. So then it will be for x1 1 state, then 2 2, that will be root 2 minus 1 into k2. So this will be one eigenvector. Okay, next we have to find for lambda 2 equals to minus root 2. So this is for plus root 2. Okay, so this is for the plus root 2. So this is one option. So this is for a higher eigenvalue. For larger eigenvalue, we get 1 plus root 2 minus 1. This is same option. Okay, now we have to minimize the option. So for lambda 2 equals to minus root 2 alpha, that is for smaller eigenvalues. For smaller eigenvalues, what will be the eigenvectors? again lambda alpha minus of 2 root 2 alpha, so it will be plus root 2 alpha 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 minus alpha plus root 2 alpha into x1 x2 is 0 0. Okay, so from here we can find that alpha into 1 plus root 2 then x1 and plus alpha x2 equals to 0. So easily we can say that for x2 is minus of this, so what will be the eigenvector? Eigenvector will be 1 then minus 1 plus root 2 into, so option B will be the correct one. This is 1 minus root 2 plus 1 and get 2, so option B is the correct one. Next 2014 again. So now we can write this state at t equals to 0 like this way, that is psi of 0 is nothing but linear superposition of these three states, so Cn get psi n. Okay, fine. So if we want to find this wave function at any time t, it will be for 1, that is C1 in psi 1 e to the power minus iota e1t divided by h cross plus C2 e to the power C2 psi 2 e to the power minus e2t by h cross and plus C3 psi 3 e to the power minus by h cross e, it will be only e and also only, okay, this one is e minus 3g into t. Okay, so this is the psi of t. Okay, now we can remove this part, or okay, leave it, we can remove this part at last. Okay, now what will be the amplitude? Okay, there is a probability amplitude. Now we have to find the probability for this state now, so we have to take out the probability amplitude, that is capital A. So capital A is nothing but psi final then psi of t. So this is the inner product of psi of t with psi of f, that is the final state. Okay, now if we want to find these things, what will be the actual result? Now actual result will be for this phi 1 is 1 minus 1 0. So if we multiple scale, if we do inner product with these two, then it gives 0. Okay, so first term is 0. Second term, this is the phi 2, so phi 2 is what, 1 1 minus 2, so it gives only minus 2. So therefore it will be C2 times minus 2 divided by root 6. Similarly, then exponential term as it is e to the power minus et by h cross. Okay, for the third one, this is for psi 3. Psi 3 is 1 1 1. If we take inner product with these two with psi f, then it gives only 1, so 1 by root 3 then e to the power minus iota by t into by h cross into e minus 3g into t. Okay, fine. So this is the probability amplitude. Now we have to find out what is the actual probability. That means we have to square it. Okay, take the mod square. Before that we have to substitute the c1 c2 c3 values, that is the coefficient values. So here c2 is 1 divided by root 6, so root 6 into root 6 it will be 6 only, so minus 2 by 6 is minus 1/3 plus here we get c3 is root 3, so it will be 1/3 again, then e to the power it gives 3gt by h cross with iota, and we take common out this part. What is the part? This is the exponent energy part only. Okay, that is e to the power iota et by h cross. Okay, now if we want to find out the probability, that is the magnitude of a squared. Okay, so magnitude is a star a. So magnitude of a squared, that means a star a star into a. Then this term, this this global phase will be cancelled. Okay, so only this part will remaining. Okay, so it gives 1/3 into 1/3 into e to the power iota 3gt divided by h cross minus 1. We have to multiply with the same things with the negative sign. Okay, same things with the negative sign. So or we can also take common out one part from here, and then easily can use the form. Okay, so if we take, okay, no problem, we can multiply directly. It is e to the power minus iota gt by h cross 3gt, 3 is there, 3gt by h cross minus 1. Okay, so it gives 1 by 9. Okay, it gives 1 by 9. If we multiply them, first term gives 1, second term this as it is, third term minus of this, and last term again plus 1. So it gives what? 1, and this term will be the cos theta value. Cos theta is what? Cos theta is e to the power I theta plus e to the power minus I theta by 2. Okay, this is the cos theta. So if we write this term, so this term minus 1, again minus 1, if we take minus 1 common, and if we dividing a whole term by 2, then we have to multiply again 2. Okay, then here we get e to the power 3 iota gt by h cross plus e to the power minus 3 iota gt by h cross divided by 2. That is nothing but cos theta. So it will be 2 cos of 3 gt by h cross. Okay, so 2 minus 2 of this, so we can take common out 2 here. This is 2 by 9 of 1 minus like cos theta. So it gives what? It gives 2 cos square theta. It gives 2 sin square theta. That is cos 2 theta is cos square theta minus sin square theta. So obviously 1 minus cos theta will be 1 minus 2 cos theta will be 2 sin square theta. Okay, so here we get 2 by 9. It will be sin square theta by 2. Now theta is what? Theta is 3gt by h cross. So it will be 3gt by 2 h cross. 2 by 9, 3gt, 2 by 9 sin square 3gt by 2 h cross. 2 by 9. Why 2 by 9? Sorry, here there will be another 2 for this formula. So it will be 4 by 9. So 4 by 9 times sin square theta by 2, that is 3gt by 2 h cross. So option B will be the correct one. Okay, next one from 14 again. So ABR operator share all eigenstates. Okay, then the least possible value of this product del B and del A. Okay, now when two operator have simultaneous eigenvectors like here A and B, then their commutator always 0. That means they can commute with each other. Okay, so in generally the uncertainty product of these two operators in general formula gives that will always get equal to half of mod of expectation of AB, commutator of AB. Okay, this is the formula. Now since here A and B share all eigenstates, that means that physically indicates that we can measure A and B simultaneously. Okay, so commutator of AB will be 0. That means del A and del B gives 0. This is the least possible value for this product. So option B will be the correct one. Next one. So for harmonic oscillator, wave state wave function is given. Okay, and here alpha is constant. This is alpha, and this is A. Okay, A dagger, that is the rising operator. So alpha is a complex number. Okay, no problem. So what is the probability that the harmonic oscillator is in the n state? So very simple. See, for A dagger, if we operate A dagger rising operator on any state, say n state, it gives always root under n plus 1, then n plus 1. This is the things for A dagger operator. It increase the level. Okay, now for this case, that is a psi e to the power minus mod alpha squared by 2, then e to the power alpha A dagger, then 0 state. So what will be the exact output for this state? Okay, so now see, for exponential e to the power x, so what is the expansion for e to the power x? Now it will be x to the power 0 by 0 factorial, it gives 1. First term it gives 1 only, so 1 plus x to the power 1 by n factorial 1 plus x to the power 2 by 2 factorial, and so on. Okay, so now if we replace this x by any operator like A, then it will be, first term will be an identity matrix, second term will be only A, third term A squared by 2 factorial, and so on. Similar way, if we write this term, that is e to the power alpha A dagger, that means in general the expression will be summation x to the power n by n factorial, n equals to 0 to infinity. So we can write this term similar way, that is summation n equals to 0 to infinity, that is alpha A dagger to the power n divided by n factorial. Okay, now since here n is, sorry, alpha is a constant with having complex identity. Okay, so we have to take always magnitude of alpha. Okay, we have to take always magnitude of alpha, so it gives nothing but summation n equals to 0 to infinity mod of alpha, then A dagger to the power n divided by n factorial. Now whenever we operate A dagger on 0 state, so this is as it is term minus alpha mod square by 2, and if we break this term, so if we break this term, that is summation n equals to 0 to infinity mod of alpha, then okay, mod of alpha, okay, no problem. So mod of alpha, then n factorial in denominator, A dagger to the power n, it operates on 0. So what will be the answer? Now we can break this term, and since we have to find out the probability that the harmonic oscillator is in n eigenstate, so we take the inner product with this, that means only n bra n with k10 only gives 1, and others, for others case like 0, 1 and so on, gives 0. So ultimately we can find out the probability for the n state only when we replace this by n. So if we replace this by n, so it will be root under break it into like n state, it will be 1 first, second, 2, third, 3, fourth, 4 and so on, and the constant term, the coefficient term, we'll get like root under 1, root under 2, root under 3, root under 4, like this. So if you want to break it, then it will be e to the power minus mod alpha squared divided by 2, and then it gives mod alpha divided by n factorial, and here we get root under 1 like root under 2 and so on up to root under n. Okay, and for n state only we can neglect the all other term, all other state, because we have to find out only the probability for this state, and for n bra n ket n only this gives us 1. Okay, so for other all state it gives 0. So that's why we are neglecting all other states. We are only considering the n state only. Okay, so it will be ket n. Okay, so this is nothing but n factorial, root under n factorial. So ultimately we get e to the power, so when we okay, this is the thing. So alpha mod square divided by 2, then mod alpha divided by n factorial, then root n factorial, so it gives root under n factorial into n. Now we have to find the the expectation value, okay, for this state, sorry, probability. So probability, that means we get that probability. What will be the probability? The probability will be n, or we can write psi, no problem, then psi mod square. Okay, so bra n ket n gives 1, all other terms are constant term, so we can take only magnitude square. So it first term will be e to the power minus alpha mod square, second term will be alpha squared, third term, this is the denominator term, will be n factorial, and it gives 1. So this is the actual answer. Okay, this is the actual answer. And also if we take only the nth term here, so it will be, there will be an n here. Okay, so there will be an n here, so it will be alpha to the power 2n. So option, I think A, e to the power minus alpha mod square, or alpha square mod, we can take alpha mod square. Okay, then alpha to the power 2n divided by the factorial. So option A will be the correct one. Next potential is given k r square by 2. Wave function is psi of rt. Okay, and if we change the wave function psi of alpha rt, then what will be the ratio of the average kinetic energy to the initial kinetic energy? Okay, it is also very simple. Now what is the kinetic energy operator? Kinetic energy operator is nothing but minus h cross square by twice m divided by grad square. Okay, now here we replace psi of r, also t, to psi of alpha r. That means we replace r to alpha r. So r dash is basically nothing but alpha r. Okay, no problem. Now for this alpha r, if we operated the grad operator for alpha r, so grad of alpha r is nothing but alpha into grad r. Okay, similarly if we operate grad square of alpha r, grad square of alpha r, then it gives what? Alpha square grad r, like that. Okay, now this t operator is directly proportional to grad square. So for this one, first one is for 1, the average kinetic energy when we change the psi of rt to the psi of alpha rt. Okay, so for that case we get alpha squared del r, that means is nothing but proportional to alpha squared. Okay, let this like alpha, so alpha squared. Okay, this is alpha squared. Okay, so ultimately if we take the ratio between this average kinetic energy to the initial, so T final is nothing but alpha squared proportional, and T initial is 1 if we check the variation with R, so it gives only alpha squared. So alpha squared will be the correct one. Next, again Hamiltonian is given in this form, bracket notation. Now we have to find out orthonormal. 0 and 1 states are orthonormal each other, and we have to find the eigenvalues. So simple, convert this form to the matrix form H. So first term will be 1, second term will be 0 1. This is iota and also minus iota, so it is minus iota then minus 1. Okay, check eigenvalues. So we can find it very easily, because if we take the trace is 0 for every option, trace will be 0 according to every option. Okay, but if we want to find the determinant, so determinant, what will be the determinant? The determinant will be minus 1 then plus then minus 1, so determinant will be minus 2. Okay, so determinant will be minus 2. This option B is not correct, option A is not correct. We take this option, so minus and I squared plus, so this is not correct, so only C will be the correct one option. Okay, next problem. So for the Hamiltonian of the quantum particle, this, okay, a mass having ring this. So theta is the angular coordinate, alpha is the constant, the energy eigenvalues and energy function of the particles are. So very simple. If we break it like theta, it will be wave function will be e to the power iota in theta divided by root 2 pi obviously, but what will be the energy value? If we want to find the energy value, then what will be the energy value? So let's try. So we can break these things now. So first term will be a squared minus, so minus h plus squared by twice m, h cross by twice m, then del 2 del theta 2, del 2 del theta 2. Okay, and the last term will be minus h plus square alpha square divided by twice m. Fine, and the intermediate term is plus twice iota alpha del theta. Okay, so for simply we can conclude that, so the wave function is obviously e to the power iota in theta divided by root 2 pi, but what will be the energy? If we find the energy, if we want to find the energy, then you will get that there is always a term that is minus alpha h cross square alpha square by twice m. Okay, minus h cross square alpha square by twice m, but it is plus na. Okay, it will be plus. So from here we also get this term. Okay, for every option we get this term. Okay, but for these two, first term and the last term, for first term and last term, can we get these same things? 2n alpha. Okay, we can solve this by taking the option. Okay, trial method. Let's take this option A. Okay, we have the wave function psi n of theta. Okay, then fine. So h psi equals to e psi. So h is what? This is the h. Psi is, we take e to the power iota in theta by root pi. So operate on this. So first term will be minus 1 by root 2 pi, 1 by root 2 by, both sides we can cancel out. This is psi and this is also psi. So time independent Schrodinger equation. So minus h cross square divided by twice m del 2 del theta 2 into e to the power iota n theta divided by root 2 pi. Sorry, we can cancel this part now. So then this is as it is. This is it will be twice I alpha del theta of what, e to the power iota n theta. Okay, fine. Then h cross square alpha square divided by twice m, then this part psi, and here this part e into psi, like okay, let's this term. Okay, since we cannot cancel here because psi is there. Okay, now derivative 2 times here, so 1 by root 2 pi 1 by root 2 pi. Okay, so minus h cross square divided by twice m 1 divided by root 2 pi. If we take first derivative, then it gives in e to the power in theta. Second, it again gives in, so ultimately it gives minus n squared e to the power in theta. Here it gives in, so 2I into in alpha, then again the psi, then h cross square alpha square divided by twice m psi, then here e psi. Okay, so this is the psi one na, so plus h cross square n squared by twice m, this is psi, then here it gives minus 2n alpha psi plus h cross square alpha square by 2m into psi equals to e psi. So ultimately we get e is nothing but h cross square alpha square by 2m, so we can take h cross square alpha square, h cross square divided by twice m common out. Okay, from here there is also for the